In the previous part, we talked about machines, i.e. dynamical systems. What if we now consider a set of many identical machines, or perhaps a single machine at multiple instances of time? This ensemble of machines is going to show a certain variety of distinguishable states. If a single machine can be in either of two possible states, then n of these machines will have 2 to the n possible states. Thus, the n is the base 2 logarithm of the number of possible states, and it measures the entropy of the machine in units of bits. The entropy quantifies the total amount of information that can be obtained from a machine. If the entropy is lower than it could be under some condition, the machine is said to have redundancy or constraint. Thus, if we consider a machine described by a vector, we know that its entropy cannot exceed the sum of the entropies of the individual components. If it equals their sum, then the components are said to be independent, meaning that they do not impose any constraint on each other. Let's now look at how the entropy is affected by different types of transformations. For the 1-1 transformation, it stays constant. For the 1-many, it increases. For the many-1, it decreases. And for the many-many, some subsets of states might increase it while others can decrease it. From all of this, it follows that for closed single-valued transformations or determinate machines, the entropy cannot increase. In the previous part, we also mentioned the diagram of immediate effects, which shows how the elements of a dynamical system are interconnected. But we can now state that the connections represent actual channels of communication, the messages which are communicated being the states of the elements at each step. In this example, for instance, x1 acts as a source of information for x2. This means that for any state that x1 can take as a parameter, x2 can have up to as many transformations. Thus, if x1 can have m1 states and x2 can have m2 states capable of being scattered over not more than m1 states, then the total scattering per step or per message cannot exceed the product of m1 and m2. In terms of entropies, this means that the entropy of x2 cannot exceed the sum of those initially at x1 and x2, or in other words, x2 cannot gain in more entropy per step or per message than the entropy of the source. And after it has gained all the entropy, it will not increase further. If both systems were connected so that there is feedback, the entropy would have not increased at all. Now imagine that our x2 is itself a source of information for an x3, so that x1's effect on x3 has to be exerted through x2 and is thereby delayed. If the entropy of x2 is much smaller than that of x1, then even if x2 gains all the entropy from x1 at the start, x3 can only gain entropy in increments of h of x2. This defines the capacity of x2 as a channel of communication. Of course, you can always increase the amount of information transmitted by simply increasing the number of steps taken or messages produced. If we know the time interval between these, we can also find the entropy per unit time. Decrease this interval, or equivalently increase the rate of transmission, and more information will accumulate within a given time. But for a proper initial source of information, we must have an indeterminate machine, the so-called stochastic transformation. How exactly can we represent such a transformation? Well, let's go back to the transition matrix and this time replace all the minuses with zeros and all the pluses with some numbers which can vary between 0 and 1 and whose sum per column is equal to 1. What we have now is called a matrix of transition probabilities. Each number gives us the probability of transitioning from one state to another. These probabilities correspond to the relative frequencies of different possible events. If the probabilities remain constant over time, the transformation is said to form a Markov chain. Consider an ensemble of 100 machines, which can be distributed in 4 states and which change according to some matrix of transition probabilities. Let's say the ensemble starts with all 100 machines in state A. As we apply the transformation, we obtain a new distribution, and if we keep applying it, we may eventually reach an equilibrium distribution for which there is no change. The equilibrium values of a Markov chain are readily computed. But what if the stochastic transformation doesn't form a Markov chain? Then it might be brought to Markovian form by redefining the message, by allowing it to act on vectors formed by sequences of past states. In that case, the machine is said to possess memory. When we think in terms of a Markovian machine, we have a more accurate way of calculating the entropy. Per column, the entropy is minus the sum of each probability weighted by the logarithm of that probability. This is the entropy per column or per initial condition. The total entropy of a transformation can be found by taking the weighted average of all these entropies, each weighted by the equilibrial proportion of the state corresponding to that column. If all the probabilities are equal, then the machine has zero redundancy, and the entropy is equal to the maximum, namely log m. If we go to the other end of the spectrum so that we have zero entropy, then the redundancy is a maximum. Thus, we can quantify the relative redundancy as 1 minus the relative entropy, which is the ratio of the actual entropy to the maximum entropy. In the case of zero entropy, all the probabilities will be stacked up in the same place instead of distributed in the whole column, and that single probability will be equal to 1. Then we will really be dealing with a single-valued transformation, not a stochastic. From this we can conclude that the determinate machine is a special case of the Markovian. We can visualize some of this if we represent a single distribution as a function of a variable, be it discrete or continuous. In all cases, the distribution has to be normalizable, i.e. adding up to unity. For continuous variables, we simply replace the transition probabilities of the discrete case with a probability density and turn the sum into an integral. After normalization, we can compute the entropy. Zero entropy corresponds to a single spike, while maximum entropy corresponds to a uniform distribution. Now, a distribution can also span over multiple variables or the entire phase space. What is interesting is that in the continuous case, the maximum entropy is simply proportional to the volume of the system in phase space. Now we can finally talk about noise. Consider two transducers, a transmitter which performs some encoding operation and a receiver which performs a decoding or inverting operation. Basically, we are trying to invert and recover the original message which was given to the transmitter. The condition that needs to be satisfied for the receiver to be a perfect inverter is that the transformation of the transmitter has to be 1-1. But if any extra unwanted input is added to the channel so that the input from the transmitter is not uniquely deducible from the output of the channel, then we say we are dealing with a case of a message corrupted by noise. The whole channel will therefore act as a many-one transformation, which is irreversible. The irreversibility means that the entropy is not sustained, and there is less information to be extracted by the receiver. A suitable way of measuring the degree of corruption is by taking the probability of each combination of input and output for the channel, finding the entropy of this probability distribution, and then subtracting the entropy of the distribution over the possible outputs. This measure is called the equivocation of the channel, and the entropy of the source minus the equivocation represents the actual information that gets through. Its maximum represents the channel capacity in the presence of noise. The expression here is in fact equally valid for both the discrete and continuous cases. One can see from this that one need not require zero equivocation for error-free transmission, because one can always arbitrarily increase the entropy of the source.